If you decide you need more food, feel free to get some.
If I decide.
But move quietly, not disruptive. All right. One of the questions on your little quizzy poo was find a unit vector. How many groups think you accomplished that you found a unit vector? How did you do that? How do we make a vector into a unit vector? Mr. Keller? Well, divided by its magnitude, which is the hypotenuse if you draw it. So I'm going to look at this vector, 3, -1. What is the magnitude of that vector, 3, -1? What is its length right now? Square root of 10. Square root of 10. Now, if I want to make that a unit vector, I would simply divide everything by the square root of 10. So the unit vector would have coordinates 3 over root 10, -1 over root 10. That's the unit vector, which means that guy now is how long? 1. Now I'm wanting to be 8 units long. So to shrink it, to make it 1 unit long, I divided by root 10. How do you think I'm going to make it 8 units long? I'm going to times it by 8. Now, I don't times the original vector by 8. I multiply the unit vector by 8. So the vector in the same direction with a magnitude of 8 is right there. You can make a vector have any length you want it to have by first changing it into a unit vector and then multiplying it by whatever length you want. Okay, guys? All right. Next. All right, I think there was one sort of like this on your thing too. Let's think about this for a second. All right, so what have I done? I want vector AC, I want the vector from A to C to be equal to the vector from D to B. That's what the problem says. I want those guys to be equivalent vectors. I want them to be equal. Now I know that A is 1, -2, and C is -1, -5. So what are the coordinates of AC? This is fundamental. You need to be able to do that. AC is what?
2.
-2, -3. Now, I don't care how you figure that out, but you've got to understand that 1 to -1 is back 2, and -2 to -5 is back 3. Now, if these are going to be equivalent, that is exactly how this guy must move. So in getting from here to here, he has to back up 2 and go down 3. Well, I know where he ends. So I need to figure out where he starts. So where does he have to start? So that if he backs up 2, he'll be at -3. -1. -1, back up 2, put you at -3. Where does he have to start? So that if he backs up 3, he'll be at 4. 7. There it is. There are the coordinates of point D. Easy questions. Easy. All right. Now we have these 2 people. We even know how old they are. And we know their puppy is strong and stubborn. We know his name. And they take him for a walk using 2 leashes. So we've got a situation like this. There's a dog who's pulling on him. She's pulling this way with a force of 23. And he's pulling this way with a force of 27. And we want to know how hard is the dog dog pulling, okay, so you understand what's happening? They're tugging on the leashes this way. The dog is, standing there, and nobody's moving. Okay, any ideas how we'll figure out what force that dog is exerting? Aiden?
You basically just plug in X for the line between.
Plug in the X for the Y. Where are the X and Y in here?
Just put X as a variable for its force between 27 and 23 on that line.
Did you hear?
Yeah.
Yeah, I think that's right. Think about what Aiden is saying. He's saying, okay, if we took everything else out of the picture, except for the girl, could we find the horizontal component of her vector? Okay, so he said call that X. So the cosine of 18 equals X over 23, or as we discussed yesterday, X is going to be 23 cosine 18 every time. It's going to be magnitude times cosine. Now, what about the guy? Now, his triangle is a little bit different, but can't we do kind of the same thing with that? Can we find his horizontal force? So his horizontal force would be 27 cosine 15. Now think about it for a second. These kids are both pulling on the dog. And the horizontal components of their pulling are here and here. Isn't their total horizontal pull what the dog is doing in the opposite direction? So the answer to the question is just going to be whatever those two added together are. 23 cosine 18 plus 27 cosine 15. So 47.95 pounds. So the dog's force is the total of their two horizontal forces. The dog is pulling straight back, right? The dog is only horizontal. Their forces are horizontal and vertical, but we only care about the horizontal part because that's how the dog is pulling. Does that make sense? All right, good deal. 6.1 done. Awesome. All right. You may have been wondering about vector multiplication. Anybody lay awake last night thinking about that? How do we multiply vectors? Now, we know already how to multiply a vector times a scalar. So for example, if vector B is 3, 2, and I want to know 2v, it's real easy. I just distribute the two. That's called scalar multiplication. So that would be 6, 4. We talked about that the other day. What we're going to do today is multiply actual vectors. So I have these two vectors, and I am going to find what's called their dot product. Now, in vector land, this is different than this. Now, in regular multiplication, if I say 2 times 3, if I put a dot between them, or if I put a cross between them, it doesn't make any difference, right? They're both symbols for multiplication. But in vector multiplication, this is called the dot product for obvious reasons, and this is called the cross product for various reasons. And they are totally different. First of all, you can't even dot in 2 dimensions. So we're not gonna, or excuse me, you can't even cross in 2 dimensions. There's no cross product in 2 dimensions. You have to be 3-dimensional in order to find a cross product. The other big difference is the dot product of 2 vectors is a scalar. So in other words, when we figure out how to do this, the answer is going to be a number, like 5 or something. When you cross 2 vectors, you get another vector. Okay, so they are completely and totally different. Today our focus is the dot product. To find the dot product, if you know the vector's components, it is super simple. The dot product of these 2 will be 1 times 6 plus 2 times 3. That's the dot product. So notice what I did. These were my 2 vectors. How did I find the dot product? I took x times x and y times y, and I add them up. So the answer to the problem is 12. The dot product is 12. That's very easy. All right, let's try the next one. What's the dot product of these 2 vectors?
4 minus.
It would be 3 times 8 plus negative 4 times 6. 0. The dot product's a number. This time that number turned out to be 0. Now, a lot of times in the real world of physics, we don't actually have the beautiful little coordinates of the vector, the components of the vector. A lot of times what we have is a situation where we've got 2 vectors forming an angle. So if we have a situation where the magnitude of this one's 10 and the magnitude of this one's 11, and they're forming an angle of 72 degrees, in order to find their dot product, we need a little bit different strategy. So that other strategy, there's 2 definitions of the dot product, depending on what information you're given. If you're given the coordinates, it's x times x, y times y, add them up. If you're given 2 vectors, then the dot product is the magnitude of the first one times the magnitude of the second one times the cosine of the angle between them. So the dot product can be found a couple of different ways. And one of those ways is magnitude of first times magnitude of second times cosine of angle between them. Okay, so I can type that in on my calculator. 11 times 10 times cosine 72. I got 33.99. Remember, the dot product is always just going to be a number. So in this case, that's the number. Now, the really cool part about this whole dot product thing, one of the cool parts is, we now can find the angle between any 2 vectors that we are given. Now let's think about this for a second. Can we find the dot product of these? What's the dot product here? What do we get to find the dot product? Yep, negative 11. Is that okay with everybody? But we can also find the dot product by taking the magnitude of the first vector. Okay, what's the magnitude of this guy? Root 17, thank you, Mary. Times the magnitude of this guy. Thank you. Have you guys tried how to find magnitude? Square, square, add them up, take the square root. It's the Pythagorean theorem. So our other definition that we just talked about for the dot product is magnitude of first times magnitude of second times cosine of the angle between them. I don't know what that is, but that's what I'm trying to figure out. Now notice, the dot product is this, and it's also this. So what can I do? Set them equal to each other. So negative 11 equals the square root. I'm going to go ahead and combine those radicals. What's 17 times 13? 221 cosine theta. And now you know what I'm going to do, right? I'm going to divide by square root of 221. And then what am I going to type in my calculator in order to find that angle? A second cosine negative 11 divided by the square root of 221. I got 137.73. That's a really important little skill right there. So, everybody okay with that? I find the dot product both ways and set them equal. And then I'm going to get my angle. I got my cosine. All right, would you try the next one on your own? It's exactly the same thing, just different vectors. Anna, what's going on? What have you got there? Anna?
I got, like, for the first one I got 0.
Okay, because you had positive 48 and then negative 48.
Yeah.
All right, and then you did a magnitude. You don't worry about reducing these radicals. You can just leave them like they are. So what'd you get here?
Square root of 42 for the first one.
Okay. 36 and 16, I think that's 52.
Oh my god.
And then for the second one,
Oh, I didn't do that one yet. But I can do it.
I got 208. Is that all right with anybody? Did I make a mistake?
Yep, yeah,
And cosine theta. Now, as it turns out, Anna's mistake wouldn't have made a darn bit of difference. Because when you set these equal to each other, I don't care what this radical is. When I divide, aren't I still going to have 0? Are you following me? So she'd have been okay. What angle has a cosine of 0?
90.
90. Okay, now wait a minute. wait a minute, 90. That means that these two vectors are perpendicular to each other. The angle between them is 90, so they're perpendicular to each other. I want you to look at something. This is the vector that goes up 4 and left 6. So his slope is 4 over negative 6. Does that make sense to you? Remember, that's y. That's it. This guy goes down 12 and left 8. So his slope looks like this. Now, if I simplify those, this one is negative 2/3, and this one is 3/2. Does it make sense that they're perpendicular to each other? Yeah. And anytime the dot product is 0, anytime you get a 0, those vectors are perpendicular to each other. Now, you know how we don't say length, we say magnitude, and we don't say sum, we say resultant? Well, we don't say perpendicular, we say orthogonal. Orthogonal is the vector word for perpendicular. I don't make the rules, okay? Don't shoot the messenger. Orthogonal is the vector word for perpendicular. So if somebody says to you, are these two vectors perpendicular? Well, they won't say that. They'll say, are these two vectors orthogonal? You can do two things. You can check their slopes, or you can do their dot product. Now, when and if we get to 3 dimensions, you're going to have to do the dot product. Because in 3 dimensions, there is no slope. Because how is slope defined? Y over x, y over 1. There's no room for the other dimension. So dot product is an awesome thing to keep in your back pocket, because that's how you can tell if vectors are orthogonal to each other. Okay, back up. Didn't we get a 0 on problem 1b? What's the slope of vector v? The slope of vector v is negative 4/3. What's the slope of vector u? 6/8, 3 over 4. So, yeah, those were orthogonal also. We didn't realize it at the time, but they are. All right. Now, looking at the next set of questions, you're all thinking, well, I can certainly do the orthogonal part, because if they're orthogonal, their dot product is 0, right? But what does it mean to be parallel? What can you tell me about parallel? The slope is the same, or in other words, if v, let's just use this guy, if those are the coordinates of vector v, then anything parallel to it has to move in that same ratio. So in other words, would 2, -8 be parallel to it? Yes. Would 1/2 -2 be parallel to it? I knew I threw a fraction in there, but yes. Scalar multiples are parallel. So if you have a vector, if you times it by 2, if you times it by 1/2, doesn't make any difference. Timesing it by anything will make it parallel. So you can rely on slope until you get to 3 dimensions. Then you've got to look for scalar multiples. Okay? So if one is a multiple of another, they are parallel. All right, so let's look at them and see. What's going on in A? Parallel? No. Orthogonal? Yeah. A is orthogonal because the dot product is 0, or you can say the slope of v is 3 over -1, and the slope of u is 2 over 6. Those are opposite reciprocals. All right, what about B? Yeah, isn't the second one -2 times the first one? Guys, pay attention to me. I know you're full of cookies and crap, but you gotta listen. The second one is -2 times the first one. That makes them scalar multiples. That makes them parallel. Joseph, wake up. What about V? I mean V, C. C. They're orthogonal, aren't they? What's their dot product? I'm looking at letter C. Isn't the dot product 0? I want you to think about the vector 1, 0. Isn't it horizontal? And what about the vector 0, 3? Isn't it vertical? Doesn't that make perpendicular? Yeah. And how about D? Neither. That's kind of a tricky one. Are they multiples of each other? No, not quite. Close, but not quite. So D is neither. They have no special relationship to each other. Does anybody have a question about that section? Parallel, orthogonal, or neither? All right. So now we got Juan sitting on a sled and climbed on a hill. Okay, let's see what's going on here. Sam. Okay, so let me see what's happening. Okay, so here's my hill. And climbed at 45 degrees. And okay, so here's Juan right here in the sled. He's right here. And up here is Rafaela. And you know what's going on here. Juan and the sled are trying to go down. I mean, gravity is pulling them down. But she's standing up there at the top of the hill, tugging them. And we're going to figure out what force she has to exert to stop it. Now, we did a problem like this similarly a minute ago with the dogs, remember? Where we had the two things pulling and the dog pulling the other way. All right, this is kind of the same thing, only now it's on a slant. All right, so here's Juan in the sled, and he weighs 140 pounds. So there is a force, gravity, coming straight down 140 pounds. Right? I am going to construct a right triangle here by taking a perpendicular from my gravity force, taking a perpendicular, so I have a little right triangle right there. Now, people sometimes make these problems hard. They're not hard at all. Imagine, I'm not drawing this in, but imagine if I did drop that perpendicular from 1 all the way down. That's a 45. What would this angle be right here? Wouldn't that have to be 45? Because don't these two have to add up to 90? Okay. Now, if that's a 45, isn't this guy right here a 45? And isn't this the force of the sled? And isn't that the matching force that Rafaela has to have on the other side? So I just need to find that distance right there. Well, that's easy. It's a right triangle. How can I find that distance? You can use cosine or sine. It doesn't really matter since it's the same angle. But cosine 45 equals x over 140. Does that make sense to everybody? So 140 cosine 45. Well, I could do that exactly since it's a 45, or I could type it in on my calculator. 98.99 pounds of force. She's exerting 98.99 pounds of force. has 98 pounds of force right here. So to keep him from moving, she has to be pulling with the same amount of force in the other direction. I think it's cool. I wish you did too. All right, let's look. Now we got a car parked on a hill. All right, so here's the hill. 12-degree incline. Here's the car. Obviously, the car wants to roll down the hill. How much does the car weigh? 2,000 pounds. So the force of 2,000 is pulling him straight down. Clayton, yoo-hoo. Open your eyes. Sit up straight. Thank you. As I always say, Clayton, if someone were walking by and saw you, they would think I was boring, and you know that's not the case, right? All right. So here we go. Here's the car, 2,000 pounds, straight down. All right, let's construct a little right triangle here. Because this right here will be the force of the car, or of the car rolling down the hill. All right, now, let's think about angles in this little triangle. If I drop this all the way down, how big would this angle right here be? 78. And if you wanted, this one would here would be 12. These are similar triangles, always will be. And I want to know this right here. So depending on which angle you want to use, and it makes no difference whatsoever, we have cofunctions, and so whatever angle you use doesn't matter. If I want to use cosine, I'll say cosine 78 equals x over 2,000. I could also do it with sine 12. So the force of the car pulling down the hill is going to be 2,000 cosine 78, 415.8 pounds. So if you're Tarzan keeping that car from rolling down the hill, you're going to have to exert 415 pounds, right, to keep it from moving. All right, I thought there was a second part of that. Yes, the second part is find the force perpendicular to the street. So this would be the force perpendicular to the street. Well, I can use sine 78 or cosine 12. It doesn't matter. You can use whichever of those angles you want because you got them both. So if I use cosine 12, it'll be y over 2,000. So that force is 2,000 cosine 12. Now kids, it doesn't matter if you use sine or cosine in this triangle. Okay, it's going to depend on which angle you're using. So I got 1,956.30 pounds for the force perpendicular to the street. Alana?
So if we would have used the cosine 12 one first, would we have done the cosine 78 one second?
Well, if you do cosine 12, you're finding this. And that is not the force keeping the car from rolling down the street. That's the force perpendicular to the street.
Okay.
So it depends which side of the triangle you're trying to find. All right. Now these problems, talking about forces and the amount of effort we have to exert, kind of bring us to a little conversation about the physical concept of work. anybody ever talk about work in a physical sense before? I mean, in a, like a physics sense? Anybody know what it is?
That's our good last.
Work can be calculated by taking the force times the distance times the cosine of the angle between. So, when you think back to the dog problem, we knew the magnitude of the force, we knew the cosine of the angle between, or we could find the cosine. We didn't know what distance they were pulling the dog. But if you know those three things, you can calculate the work. So let's see if we can answer question 6. Pretend I'm really strong, and I'm going to pick up a car and lift it straight up in the air 5.5 feet. How much work have I accomplished? Well, the magnitude of the force is the weight of the car, which is 2,600. The distance I am moving it is 5.5 feet. Now think about it. What is the angle between the force, which is lifting it straight up, and the distance, which is a vertical distance? The angle between those two is 0. Aren't they both vertical? Isn't the force vertical and the distance vertical? So that's the cosine of 0. What's the cosine of 0? 1. Cosine of 0 is 1. So, if the force and the distance happen to be in the same direction, then you don't worry about the angle. The angle's not important. So the amount of work done, real simple, 2,600 times 5.5. And believe it or not, there's a unit on that, and the unit is foot-pounds. Because we lifted the car 5.5 feet, and it weighed 2,600 pounds. Two more and we're done, maybe. No, we're not going to get them both done. All right, let's do one more. One more. Find the work done by a force of 12 pounds. Okay, so we got 12. Acting in the direction 1, 2, in moving an object 4 feet. So we know the magnitude of the force, and we know the distance. It's going from 0, 0 to 4, 0. So here's 0, 0, and here's 4, 0. So the force, or excuse me, the distance is horizontal. Everybody okay with that? And the force is acting in the direction over 1, up 2. So here's my force acting in the direction over 1, up 2. Now wait a minute. If I have a horizontal, and then I have this thing that has a slope of 2 over 1, can I find that angle? Can I find the angle between the horizontal, which is my distance, and the force, which is over 1, up 2, according to the problem? Can I find that angle? How would I find that angle? Second tangent, 2 over 1. So second tangent, 2 divided by 1. That angle is 63.43. of that, and I'm gonna take the cosine of that angle times 12 times 4. And I get my work. What did you come up with?
21.47.
Yep, 21.47.
Isn't the cosine of that angle just one, or root 5 over 5?
Oh, wait a second. Sam says, because he's a genius, his eyes are open for a change. He said, wait a minute, Mrs. Ford, you already drawn a picture of the angle. We know that's 1, that's 2, this has to be root 5. So isn't the cosine of the angle just 1 over root 5? Right? So the exact answer of the problem would be 12 times 4 times root 5 over 5, or 48 root 5 over 5. Very, very good, Sam. Very good. If you have already drawn the right triangle, then you know what your cosine is, and we could actually do that problem without a calculator then. That's not always going to be possible, but it sure was on this one. Nice work, Sam. Good problem. All right, well, we have one more to do, so we'll finish 6-2